And we are live, and thank you again. I know there's a lot of other great sessions to choose from, so thank you for stopping in on this one. Okay, so I'm going to proceed. This talk is being delivered to a live audience, so I'll be taking questions at the end. Volunteers have been kind enough that they're going to collect the questions in the private chat, so I'll address them if there's time at the end. Otherwise, I'll be in the Remo conference software at room 1, table 1. Okay, so I look forward to your discussion there. Okay, so the abstract that you've seen and hopefully drew you into this talk is here, so you've already read that. Just a little bit about me, your speaker. So you know me, the highlights in orange here. I'm an assistant teaching professor at Northeastern University. I do research primarily in performance. I also do some consulting in computer graphics work, various 3D projects. And if you want to find out more about me, you can read this later or visit my website. Okay, so what are you going to learn today? Just so you know what to pay attention to. Today, you're going to learn what design patterns are and why you should study them from a sort of pragmatic viewpoint. I'm going to be walking us through some live coding examples so you can see just how I think about design patterns and how you can apply them. So we're going to use a creational pattern, implementation and use of it, do the implementation and use of a structural pattern called the adapter, and then how to use a behavioral pattern. These are, we're going to look at iterators in C++. Okay, so my expectations are, if you're watching this talk, is that you have written some C++, you understand some of the basics about things like memory allocation, object lifetime, and so on. I'm also expecting that you'll know a little bit about object-oriented constructs, things like classes, structs, encapsulation, polymorphism, inheritance, composition. All these good things should be familiar terms for you. Okay, so with that, let's dive in. Let's just start building some software. Okay, so I want to give us a running example to motivate design patterns today. And the deal is, you've been hired as a programmer to perform some maintenance. Okay, so you're going to join an existing company and you're going to work on this exciting new screensaver software. So some actual code that you're going to see. And you're going to get lots of money if you do a good job. So you want to be a good software developer and implement some of the best practices. Additionally, this is a well-established team, and you're going to be working with a large team, many different colleagues of many different levels. And if you do a good job, you're going to get hired to do another contract and get to do some more work and keep producing some cool C++. So if that sounds good, sign the dotted line and let's go ahead and proceed. Okay, so your first day of work here. So here's what you're given. It's a screensaver. So on the right of my screen here. And you've got a bunch of circles that are bouncing around here to give that sort of classic screensaver effect. Now your job's going to be to maintain and improve this software. And as I'm looking at this, the initial effect looks nice. We've got the visual sort of moving around in different directions. It looks a little bit random. But there is a subtle error if you watch it for long enough. And the error is that all of the circles start out at a fixed portion of the screen, which I've highlighted on the right here. So you'll notice as this animation loops, all of these circles are grouped up here. And once you notice it once, it's hard to unsee. So it's kind of a bug here on your screensaver software. So good job, you've spotted your bug in the software here. So you go through, start looking at the code, and start doing some bug hunting here. Okay, so here I have on the right a constructor for each of these circle objects. And you notice that the starting position of each of these circles is randomly generated to create a more interesting effect. But you notice the range is a little bit peculiar, that your X and your Y position of these circles is a range of 1 to 300. Okay, and that's fixed. So we see this sort of fixed value here of 300, 300. There's no documentation, and we don't know why it's set like that, but here it is. And then you do some more investigation, and you observe that the actual window where you're drawing that screensaver has a window width of 640 and a window height of 480. So you discover these global variables that are sort of setting a bounds for how big our environment is. Okay, so that's most likely the intended range of where you wanted to sort of randomly spawn all of those circles to get a more smooth screensaver effect. Okay, so great, we find the actual bug. So let's try to fix it. Let's be good software engineers as we've been newly hired for this company. And deadline's coming up, so let's do a quick fix here. Let's just adjust the range. So it's now 640 by 480. Problem solved, it's going to look just as good and have the intended effect that you wanted. Okay, but when we do these kind of quick fixes, we're merely masking the bug or making it temporarily go away. Because what if we change the window size again or have to get a bigger monitor with a different resolution? Okay, so now we have to maintain this value in two different places. And not only do you have to remember, but other software engineers who are working on this project have to remember as well. So in this first spot, I have to remember 640 by 480. And then in the second spot, I have to remember 640 by 480. Okay, well, you might say to yourself, the point of having global variables, after all, which we've defined down here, window width and window height, is to take care of this problem and to try to solve having different values in different places remain consistent. But things can get a little bit messy when we start using global variables in our files. We have to maybe include them in a header, and then if we bring somebody else's third-party code in and they name them the same values, there's symbol resolution issues we have to deal with a linker. So things kind of get a little bit messy when we start having these sort of freestanding globals together. And even more so, window width and window height are related. So it would be nice if we could remember to group them together in some way. So there has to be a better way to do this and to solve our bug. Okay, so this is where I want to introduce design patterns, or at least a pattern that can help us with this problem. So design patterns are common repeatable solutions for solving problems. You can think of them like templates or some sort of blueprint for developing software. They've been tested before. Someone else has implemented them and had a success story that they can share. This is the idea of design patterns. So design patterns can help us as software engineers write software that's more flexible, maintainable, and extensible. Okay, and these are likely qualities that we want to have on a software engineering project over a long term, especially if it's a big project, if it's evolving, and if it's collaborating with multiple parties. We want to have all these characteristics, or as many as we can. Design patterns are one way that can help us. So the origin of design patterns goes back quite some time. Folks say at least the term goes back to the 70s. The term design patterns from a reusable elements of design in an architecture book, this book, A Pattern Language. That's where various patterns were founded for different architecture patterns, so different industries. So that's where the term comes from. Where a lot of the popularity, or at least where I have learned about design patterns comes from, was from a book that came out in 1994 known as the Gang of Four book for the four authors that sort of categorized and listed a lot of the most famous design patterns. So it's popular enough. There's a Wikipedia page where you can learn more. There are C++ and Smalltalk examples included, but you can apply them to many languages, and we've seen that over time has been true. And this is really a good starting point for design patterns in object-oriented programming. So the book's a great resource where you can learn more about the patterns that we're going to talk about today. A brief aside, a book that I've really enjoyed is there's another book called Game Programming Patterns that also has a free web version if you want to get started right away. I also have a physical copy because I've really enjoyed that book. So both of these books, whichever you decide to jump into, have some reusable templates to help us solve problems that keep reoccurring in software. And again, what this design pattern book does a nice job doing is categorizing the design patterns into three categories: creational patterns, structural patterns, and behavioral. So there's three categories of design pattern. We're going to look at one design pattern in each of these categories throughout this talk. Creational patterns, the general idea is that you're providing your program more flexibility in how you create the objects. That is that you're giving more control over how some objects instantiated or created, or just removing how you have to think about that problem. Structural design patterns have to do with using inheritance or maybe composition to get new functionality. And behavioral patterns focus on how communication is done between objects. That's the high-level idea of each of them. Okay, so I'm going to help us pick the first pattern to solve our original problem with our screensaver for the job that we've been hired to do. And this first one is a creational design pattern. Okay, so creational design patterns, again, deal with how objects are instantiated, often providing some sort of abstraction in the process. Meaning you can call a constructor or some member function, and it'll just take care of how the object's created. It'll figure out what the object is, what the type is, maybe some default values. That's the idea, to remove a lot of that thinking that goes on with the creational design pattern. Or rather than remove the thinking, just make it so it does the right thing that you intended. Okay, so let's look again at the problem that we're trying to solve. We want to be able to reference this window height and window width here, ideally globally. But we only want one instance of these values to keep track of in case someone names something similar. And we want them to sort of be grouped together, window height and window width, since they're related. Because maybe we'll want to write some behaviors that compute maybe an aspect ratio or things that'll be useful for dealing with window size or general configuration settings. Okay, so let's take a look at the Singleton pattern. So the Singleton, the main idea is that it's going to enforce the existence of only one instance of an object being created. So this is like a global variable where we only want one value in general, but this is going to enforce that existence. Okay, so again, this means we can store all of our configuration values in exactly one place, know exactly where to find them, and make sure we don't have duplicates or different values. Okay, so here's the pattern again. Common use cases for the Singleton pattern, where I've seen it in the wild, or typical use cases you'll see when explaining the Singleton pattern, are managing files. So a file system, ideally you just have one. And sometimes this is thought of too with a sort of resource manager. So maybe you're managing specific types of data, like loading images or audio files, and want to make sure you only load one copy of those files. File loggers, so if you're doing some debugging or just outputting text, usually you only want, or you might only want, one instance of those loggers to put messages in a centralized database. And also configuration manager, which is what we're going to build. Just hold some global configuration value that you want the same. So this is what we're interested in. This is the option that we want. Okay, so let's actually do some refactoring and solve the first task here. So the first task, or the first thing that I want to do, is from our code actually remove this global variable. We're going to remove it from where it was standing, whatever C++ file, doesn't matter. But we want to move it to a standardized location. And again, I'm moving both of them together because now they're sort of grouped together, which is nice. So we're going to move our globals from one file and build a new class called the configuration manager. I can name this whatever you want, but something standard. So the configuration manager is going to be our demonstrate our Singleton pattern, where we'll just access and share data in one place. Okay, so let's take a little closer look at the C++, since we're here at CppCon. Starting from the bottom, we have our window width and our window height. So those are the two variables that store the window width and height that we want to keep track of. I've prefixed them with m_ because they're member variables now of a class. That's just a hint for me stylistically. In order to access our member variables, then I've also written some getter functions and setter functions. just to make sure we can access these as needed. And the real interesting part of the Singleton pattern comes here. You'll notice I don't really have a constructor, or I do have one, but it's actually been marked private here. So the constructor and the destructor, in fact, have been hidden. But what I do have remaining is one public function here called instance. An instance is going to be in charge of handling how an object is created or used in the Singleton pattern. So just going line by line here, at the first line, I have static configuration manager. So this is going to create some static pointer here to configuration manager and allocate a new one. Now in C++ 11 and beyond, we have this guarantee that we'll only have this initialized, this static variable initialized once. So I could rewrite this as if configuration, if some instance is null or so on, and have a instance variable here, but I've chosen to just sort of use a modern style here. But this is going to allocate our new instance if it hasn't already, and then any time that we use instance, it's going to return that instance to us, a reference to it. Okay, so now if we work through this instance function, we'll always be working with the same instance of this class, which holds this piece of data here, our window width and our window height. Okay. Okay, so now we've successfully encapsulated how an object's created, and we've restricted this access to just create exactly one instance of the singleton. Okay, and that's what our configuration manager is doing. It's now satisfied that singleton pattern. Okay, so here's an actual example of using the singleton, again, because we're trying to solve our problem, and just how to use our member functions through the instance member function. And again, because we're always going through that same instance here that's returned, we get the same values. So in my configuration manager, I might do a little bit of setup somewhere in my program and set the window width and the window height as needed. And then anytime I need to access the window width and the window height, I can get the same value by doing the configuration manager, calling the static member function instance, and then returning its width. Okay, so let's actually solve our problem. So in our circle constructor, where we had those hard-coded values previously, we can now access through the configuration manager here. So configuration manager instance, get the window width and the window height from here. And all I've had to do is include the configuration manager header file to do so. Okay, so let's see for a moment if this solved our problem. Our fingers are crossed. And if you watch this animation from the start, you'll notice we have circles that span the whole range of a screen. So I'll let it play one more time here just so you can see from the start. I give a little, you'll see a little countdown message here, and you should see circles spawning all over the place. And you're going to find it's much more visually appearing. So here we go, and voila, much better effect. Your boss and your colleagues are much more happy to see this. Okay, so let me wrap up our first pattern on the singleton. So some pros and cons with design patterns, because something I want to talk about is I'm going to give you some recipes or some templates that you can use in your code, but you have to apply them in the right place. And you have to understand, as with everything in computer science, there are some trade-offs for when to use something versus when not to use something. So the pros for the singleton, in general, it's easy overall to implement. You saw how I used that one instance member function to access the same object that had been instantiated. And you also saw that I hid the constructors and did some work there. Overall, pretty easy implementation. And this can be effective when you know you only need one of something. Conventional wisdom says not to use global variables, but sometimes you need to. There's valid reasons to. And when you know you only need one of something, singleton pattern can be good for this. When you use the singleton, you're also avoiding polluting the global namespace with lots of variables. So instead of having lots of variables like window height and window width and these sort of freestanding variables of primitive data types, the global namespace gets a lot less polluted, so it's easier to debug in that way. Another advantage of the singleton is the memory is only allocated if you actually use the singleton. So if you are just doing occasional logging or perhaps have a debug versus a release program where you're taking advantage of some singleton classes, you're not allocating all these variables in the heap. So that can be an advantage of the singleton. Some cons with the singleton is the wrong usage could take some refactoring, meaning, if you actually do decide, hey, I need 2 loggers because I'm going to do something with threads or whatever, then you do have to do some refactoring and think about how you're going to structure your program. So again, you have to think about carefully, do I need exactly one of these objects? The singleton, as I've written it, is not necessarily thread safe. It's thread safe in the stance that when I initialized the object, I'm only going to get 1 back and should get the same 1 back. But if I'm doing other stuff within the singleton class, like logging or changing data, I'm likely going to have to add a lock or use some other atomic data structure just to make sure that I don't get race conditions, data races, and so on. So you have to be a little bit careful if thread safety is an issue. And the other con is, again, you are still effectively using global variables, so keep that in mind. You do have objects that are going to live, the duration of your program, so keep that in mind if you're going to have a really, really big singleton class. That's maybe just going to allocate a lot of stuff and not clean it up. There's a few more missing details I want to provide because I've given a singleton design pattern solution that I think works well for this use case, or at least for teaching it. But the Gang of 4 book goes through some more interesting details and design considerations that I just want to put on the table here. So in my code example, for instance, you might want to, again, think carefully about hiding the copy constructors to make this object non-copyable, because otherwise you can sort of get around having 1 instance. You'll also want to think about if a client can subclass from your singleton or not, meaning can I inherit from the singleton class and build other types from it? So that can be sort of a pro and a con, and you can prevent that if you like. Again, thread safety might be an issue. So, choose your data structures within the singleton class that you need, such as locks or atomic data structures. If you do find that you need multiple instances of a class, but you are trying to have some common ground, there's another similar pattern. It's called the monostate pattern, which makes use of static member variables. Again, the idea being that you could have a lot of shared state amongst different instances of objects. So in our example, maybe if we have multiple windows and we know they're all going to be the same height, but a different title bar, for example, we might consider the monostate pattern instead of the singleton. Okay. And be careful if you're returning a pointer versus a reference in your instance member function. It could be a gotcha. It'll still work, but a client might decide that it's a pointer, so they want to delete it and reclaim some memory. So maybe you do want that ability to delete it. Maybe you don't. Just be a little bit careful about that. So you're going to have to design this pattern up to your specifications, but you have the high-level idea now. Okay, so more on the singleton pattern. I think the game programming patterns book does a nice description, as well as the Gang of 4 book. So read both of them, see the use cases, and apply as needed. Okay, so with that in mind, I see some questions coming in, which I'll address at the end. I want to move us on to our next challenge. And the next challenge is, your colleagues and bosses and so on have been impressed with your work and your implementation of the singleton. They're giving you some more work. This time, your boss wants to put the company logo on every screensaver. Okay, so screensaver company, here it is. And it's going to be attached to every screensaver just at the top here. And your colleague and you are working on this problem, and your colleague's working on this text rendering system. Okay, and it's a legacy text rendering system. It's been around for a really, really long time. It involves a lot of work where you have to load font files. You have a custom string class in the background, some logic of sort of how you draw objects and draw text and another drawable object class. And this hierarchy is very, very deep of inheritance. And oh, by the way, the boss wants all of this text to always be green in uppercase letters, because that's going to be consistent with your company's logo and company colors. Okay, so the problem that we're trying to solve here in our second task is we have some text that must always be uniform. And this is the current interface that we have, the current data type, this text class. And this is based off of some third-party code. In fact, it's from another library called the Simple Fast Media Library, which I'll link at the end. But we don't own this, so we can't necessarily change it, or at least I, as the programmer, don't own it for my task. So there's potentially a lot of steps to fit if we want to fit our specification, meaning we had to set the particular font or the particular color and the uppercase the letters and so forth. So one possible solution you might think of is, hey, let's just write a function that we can pass this text object to, and it sets up all the proper values. And this works fine, right? We can take our reference to this text object and set the fill color, set the font size, step 1, step 2, step 3, however many steps that we have to do to get things uniform. But if we have to start changing other behaviors, that's hard to just do from the function, especially if we need to invent new behaviors on top of this particular data type. Okay, so with this idea, I want to introduce the second type of design pattern. And this is the structural design pattern, our second category from the Gang of 4 book. And structural design patterns focus on using inheritance to compose interfaces and create new objects. Inheritance, and in one case, we're going to look at one that uses composition. So structural design patterns, again, are usually focusing on using inheritance to compose different interfaces and create a new object. So in our case, we're trying to create a new text class that that satisfies our client's demands or our boss's demands in this case. Okay, with inheritance, if we're inheriting properties from another object, we get all of that object's public and protected interface and all those properties for us. So now I'm going to show a design pattern that works off that. It's something called the adapter pattern. And there's several different implementations of the adapter pattern, just like the singleton with different variations to it. But I'm going to show you the adapter pattern. Specifically, it's known as the object adapter pattern. And just like you'd visualize an adapter for all the adapters that are out there, this converts the interface of one class into another interface that the client expects. Okay, so the common use case of this is when you want to write a wrapper class to update or otherwise make some interface work. I've seen this with sort of updating legacy code bases to add new functionality. I've also seen this very often with just making various string classes work together in different libraries where you want to update things or add different functionality and just make things work. So anytime you need to wrap something up, that can be a use case for the adapter pattern. Okay, and here's the analogy just to make it clear. For those folks who have traveled across continents, you can see if you've seen a different style wall outlet, you often buy an adapter that lets you plug in your version of the outlet into a different one. Okay, so we're taking in our adapter, which is going to be sort of the adaptee, and able to plug it in by using this adapter. Okay, so again, we want to focus on the problem that we're actually solving, and that we have a class here that's been provided. It's from a third party to us as a programmer, and we don't have the functionality that we quite need. So we want to update our software, and we also don't want to break our old functionality that did exist because, again, this is a big company. You could imagine yourself in this situation, and we don't want to break this previous implementation. Okay, so first take at the adapter pattern is to create a new class. So here in this figure, I've created a class. I call it adapter text here, and this is going to be our adapter. And it's going to take our previous implementation of text and make it a member variable here. I'm just going to call m underscore because it's a member variable and the internal text. Okay, so here we're making use of composition, taking some other object and storing it in another. And inside of our constructor, it's going to take a text object as its input. That's the sort of adaptation, what I'm feeding into the adapter. Okay, that's right here. So again, just a note, there's many ways to implement the adapter pattern. You could use inheritance to adapt this. I think for demonstration, this works well for the object adapter pattern. And you have to think about some things like how deep your hierarchy is. And if you do use inheritance, that you have to potentially implement a very big interface, right? All the virtual functions that come with it, which could be a lot. So this usage of composition, this is why I've chosen composition for this adapter pattern. Okay, so here's a sort of implementation of our constructor, as well as a new behavior that we need. So I'm looking down here at this second block of code here, where I've read in my internal adapter, and then I'm going to do the things that we needed to do in our requirements. Set the character size to specific set the color. Then I've got a little loop here for making sure that all of our characters are uppercase, and then finally setting that string. Okay, so I've sort of adapted this object to fit our new interface that we need. And then this second new behavior I have is how I can draw this object. And I can add as many other behaviors as I need in my adapter, but I've added one here to actually draw it. Okay, so here's the usage of our adapter pattern. So here I'm looking at the code snippet in the top right, where we have created a new adapter text. Here's our new object that we've instantiated, and we're taking in our old text here and going to adapt it through this new object. Okay, so it's just a very quick wrapper of a previous implementation. And we see here that the text appears in uppercase. It's always green. It's the right font size. Whatever the other requirements are that you need to add can all be wrapped into this adapter text. Okay, and then as needed, you can add more functionality. No problem. Okay, so some pros and cons of the adapter pattern. Again, every design pattern has some pros and cons. The pros are, or a few of the pros are, you allow classes with otherwise incompatible interfaces to work together. Okay, so you can sort of make things work. You can grab the exact data that you need from some other class or extract it. The example I did for that, which you can see, it's a little bit subtle here, is I'm grabbing in a string the text from this class here. So that was a little bit hidden, but I made it sort of work so I could grab each of the characters, make them uppercase, and then in my new object, again, set the string here, or the internal object. Okay, so overall, this can also work very quickly. This idea of the adapter and sort of wrapping a class and adding just a little tiny piece of functionality if you just need a small piece like we did. Now, the cons for this is you may introduce more complexity into your code. So you can imagine me seeing this pattern saying, wow, that was easy. Now I'm just going to wrap every other type into its own sort of unique instance. of another data type that I need. And then all of a sudden, if you have lots and lots of different data types with just slight variations, you've introduced a lot of complexity in your code potentially. So be a little bit careful with the adapter pattern. It also might be just worth noting if you do own the code, so in our case, the text class, it might be worth it to just update that actual class if you know you'll need this functionality going forward. So again, just make sure you're solving the right problem. In my particular example, one of the cons might be, you see in these snippets, is that you might be making extra copies when you're wrapping the object. So just be a little bit cognizant of that. You might need to measure if that's expensive or ask yourself if you really need to make that copy or pass in a reference. So just something to keep in mind with the snippets that I'm showing. Okay, so with that in mind, we have our next task. So far we're doing pretty good with our screensaver company here. And we want to fine tune this just a little bit. Because we think we can be, we can improve things just a little bit more by adding some more circles. This visual effect's just not grabbing enough. It's not cool enough yet. So again, you start looking through the code and you want to go through your first refactoring. So you search through the code and you start finding for loops that look like this. For int I equals 0, I is less than 100, I plus plus. You're pushing a fixed number of temporary objects here into a vector where they're stored, and that's where all of your circles are in this screensaver. Okay, so a bunch of objects pushed into a collection. But later on, you see some corresponding code to loop through all these elements. So you see we're actually doing the drawing for int I equals 0, I less than 100, I plus plus. For the window size. Update all these circles and draw them. So there's, something interesting here, again, that you're noticing. But, you've learned a little bit from before in your coding experience that, hey, these container data structures like the vector, they have a handy .size member function, which will return, how many items are in that collection. So you can just loop through them all in this way. Okay, this is safer. This is a way to iterate through, all of the objects from a particular range. So you can do this. But I'm going to argue we can do a little bit better for this particular use case. And to do that, I can introduce our third category, behavioral design patterns. Okay, so behavioral design patterns focus on communication between objects. So our behavioral design pattern, we're going to focus on the communication between objects. And in general, behavioral design patterns are concerned with the responsibilities and the algorithms taking place amongst many similar objects. The relationship I want to work with in this example that I'm showing is just how each object in a collection is linked on how to traverse through that entire collection. So this is given, this next pattern is called the Iterator Pattern, and it provides a sequential access to elements in a collection without exposing the actual representation. So in a word that's saying is it's not going to expose how we iterate through an entire container data structure. Okay, so the Iterator Pattern. The problem is, your data structures hold some data in some type of collection, whether it's a linked list, hash table, array, a heap, a tree, some sort of graph representation, it doesn't matter. And then at some point, though, a user is going to want to iterate through and look at all the data that's in the container. So the solution that we can provide our user is to encapsulate the iteration in some way such that we have a consistent way to look through our data. Okay, so that could mean various traversals, perhaps going from the first element to the last, or reverse from the last element to the first. And depending on your data structure, these are your different traversals, like a breadth first traversal, depth first traversal, and so forth. Okay, so the sort of iterator pattern analogy is, how many possible traversals are there at Rome, by foot, walking, running by using a map, taking a tour. There's many different ways that you can look through some collection of data. Okay, so first take at the iterator pattern. And the good news about this pattern is this is one that's actually very prevalent throughout C++ in the standard template library. Okay, we often get our iterators for free, so I don't have to implement many of these if you're using the standard library's container structures. So we're going from this code snippet here down to this bottom snippet where I'm using iterators. So on this vector collection here, I have an iterator that I create, and I want it to start at the beginning. And then while my iterator hasn't reached the end of the collection, I want to move my iterator forward one element. Okay. And it doesn't look like we've done much here, but I'm going to argue that we've made some nice improvements to the code by using this iterator design pattern. So each time we iterate through, we're being very explicit here that we're starting from the beginning. That's what we meant in our old example, I equals 0, but we could make a mistake. That could change. But we really want to iterate from the start. So I have circles, our collection .begin to represent that. And then we're also maintaining, again, that we want to iterate to the very end. So our iterator here, while it's not equal to the circles .end, the end of the collection has been implemented. Okay, and this is just very explicit and clear what's going on. Again, if I have circles.size, maybe I have a size -1 or size +1, or I might forget or have that sort of off by 1 error. So again, we're just being very explicit how we're traversing through our data structure. And then finally, we're also being very clear about we want to look through everything. So we're just moving from one item to the next. In a vector or a list data structure, this is pretty clear because one item typically follows the other. But again, in a tree or a graph data structure, this is nice to have to know that we'll eventually look through everything just in some traversal. Okay, so the result on the sort of grand finale of our work is we apply this traversal. So we'll be looking through all of the circles. We've cranked the number up to 1,000, and now we get this visual here, which is a little bit more fun and interesting to look at. Okay, so with this, we've made our code a little bit more maintainable, I would argue, with this pattern. And with iterators too, we can do cool stuff if we advance the data structures. Maybe we want these circles to collide with each other and then start talking about bounding boxes and sort of partitioning algorithms on where they should, only look for circles nearby and for conclusion. So this can open the door for different optimizations later on. So this could be a pretty powerful pattern. Okay, so iterators are something you should consider using. If you look through the cpp.com reference or the cpp.reference.com, there's lots of good information on the iterators for the standard template library. Like everything else, there's pros and cons to these design patterns. The pros, a few pros that I've come up with for the iterator are, there's a single responsibility. It's very clear what the iterator should do. It should look through every element, one at a time, which is very nice. Some other things, though, that you can wrap into iterators to make them more robust is you can protect yourself from other things like insertions and removals, right? Since you have this iterator interface, which we've implemented here, based off of how I move forward or back, I can control, what happens if another one of those circles gets removed or deleted, especially in an interactive application. So those are adding some more power to iterators is an option, which is harder to do with the for loops. Some of the cons, applying this pattern could have some performance cost, especially if we're just using simple data types like incrementing integers and some of these things. So you're going to have to measure and profile to see if it's worth having an iterator and doing some of these different algorithmic strategies. So that could be some con, along with the actual cost of for your custom data structure, the cost of building, maintaining, and implementing the iterator. Okay, so I want to start summarizing what we've learned. We've looked at a small project, or we can pretend it's a very large project, and developing a screensaver with some colleagues and applying some design patterns to it, a Singleton pattern, adapter pattern, and iterator. We've seen the design patterns are very helpful. We've seen some of the strengths and where they can help us in this example. The design patterns, though, aren't always a magic solution. You've seen some of my patterns here and how I've applied them, and I've taken some liberties to implement as they make sense in each of these problems that I'm trying to solve. But again, they're a really good starting point to solving your problem and having a name to the problem that you're trying to solve so you can research further. So my recommendation is to, for those just learning, continue learning more about the different design patterns that are out there, apply them to some small projects, and test out their utility. One thing that can be helpful for design patterns is learning a little bit of UML. So I'm just going to run through a few slides here because this is how you'll often see them in the text. So I just want to make you aware of it, what it is. There's lots of different ways to diagram these things, but UML is the Unified Modeling Language. It's just a general purpose way to diagram a class and the relationship amongst objects. So you'll see these a lot in the Gang of 4 book. They can be useful to look at. So the very basic example is you'll see a diagram like this that has the class name, the member variables, member functions, and then we'll draw sort of the arrows to show if this class is derived or inherited from another class and so on. Okay, so just a quick run through of UML there, just so you're aware of it. Further recommended resources, I recommend any of these 4 books that I've looked at. Fedor gave a talk on design patterns, I think last year, and then wrote this book, which does various C++ design patterns. And these can be some excellent resources to get up and running. The code for today's talk was developed a little visualization in SFML. That's a great library to practice if you want to visualize some of these algorithms. So I can recommend that as well. So with that, I just want to take some time to thank you for attending my session at CppCon. Thank you for folks asking questions. My plan is to join folks at a table in Remo. I've got your questions that you've submitted. And thank you very much again for your time and attention today.